Good day. On today's lecture of part 221, we'll be tackling study session 2, which is measures of dispersion, skewness, and kurtosis. The second most important characteristic which describes a set of data is the amount of variation scattered or spread in the data. In this session, we shall discuss in details the various measures of dispersion and skewness. The purpose of these measures is to amplify the imperfect summary of any statistical distribution, usually provided by three measures of averages commonly used, which are the mean, the median, and the mode. These averages are inherently unsatisfactory because no single measure of average can tell you everything about a distribution, and the wider the dispersion of a given data around the average, the less satisfactory the average becomes. In order to improve your understanding of population averages, you need to know how wide the dispersion is around the average and whether it is symmetrical, that is unskewed, or asymmetrical, which means skewed. The first set of measures to be discussed here are measures of dispersion, and the second set, measures of skewness. At the end of this lecture, you are expected to be able to explain the measurement of dispersion and skewness, to use measurement of dispersion and skewness as appropriate in a practical statistics studies. You should be able to name the measures of dispersion, skewness, and kurtosis. Moving on, measures of dispersion. The common measures of dispersion include the range, the quartile deviation, the mean deviation, the variance, the standard deviation, and the coefficient of variation. The variation or dispersion can be said to measure the degree of uniformity of observations in a given set of data. The greater the variation, the more ununiform the observation in a given set of data is. The range. The range of a given set of ungrouped data can be determined from an unordered array as the difference between the highest observation and the lowest observation in a distribution. That is, the highest value minus the lowest value gives you the range. So if we say, let's say XH is the highest value and XL is the lowest value, and range is given by capital letter R, and you are asked to find the range. So R will be equal to XH minus XL, which means the highest value of X minus the highest value minus the lowest value of X. The range can be an unsatisfactory measure of dispersion because it is affected by extreme values or items which render it unrepresentative of a majority of the set of data. The quartile deviation. Unlike the range, quartile deviation does not take extreme values or items. Quartiles are the boundaries separating the items in a given distribution or set of data into quarters. There are therefore three quartiles: the lower quartile, which is at the 25% mark, the median quartile, which is at the 50% mark, and the upper quartile, which is at the 75% mark. To compute the quartiles of ungrouped data, you simply use 0.25 open bracket n plus 1 and close bracket for the lower quartile, then 0.50 open bracket n plus 1 close bracket for the median quartile, and 0.75 into n plus 1 for the upper quartile. For grouped data, you simply use 0.5n for the lower quartile, 0.5 sorry, you use 0.25n for the lower quartile, you use 0.5n for the median quartile, and you use 0.75n for the upper quartile. Here there are numerical examples, so I would prefer us to address them while in class rather than reading out figures right now. So I will skip numerical examples for when we meet in class. The quartile deviation, referred to as the semi-interquartile range, is defined as 1/2 the difference between the upper quartile and the lower quartile. Thus, quartile deviation is given by Q3 minus Q1 divided by 2. Now the mean deviation. The mean deviation can be defined simply by the following relationship: MD equal to summation into x minus x bar divided by n, where summation into x minus x bar is the sum of absolute values of deviation from the arithmetic mean, while the n is the number of observations, where x bar is equal to summation of x over n. That's the sum of all observations in x divided by the number of observations. X is the arrayed data of individual observations. The variance. The variance for a given set of an ungrouped data can be defined by the following formula. As you can see, summation of x squared minus summation of x all squared divided by n minus 1. This will be better seen and understood in class, where x represents the numerical values of the given set of an ungrouped data. Continuing with the earlier example, we will consider numerical examples when we are in class, so that you can see step by step how we go about them. The standard deviation. The standard deviation is the most useful measure of dispersion, of variation. It can be defined as the square root of the variance for a given set of data. So it means when you know your variance, you automatically know your standard deviation. Your variance is the square, your standard deviation is the square root of your variance. So standard deviation is equal to square root of variance. Variance is denoted by s squared and standard deviation is denoted by s. So to get your standard deviation, s is equal to square root of s squared. The coefficients of variation. Unlike other measures of variability, the coefficient of variation is a relative measure. It is particularly useful when comparing the variability of two or more sets of data that are expressed in different units of measurements. The coefficient of variation measures the standard deviation relative to the mean and is computed by CV equal to S over X times 100%. The coefficient of variation is also useful in the comparison of two or more sets of data which are measured in the same unit but differ to such an extent that a direct comparison of the respective standard deviations is not very helpful. An example, let's consider an example. Suppose a potential investor is considering the purchase of shares in one of two companies, A or B, which are listed on the Nigerian Stock Exchange. If neither company offered dividends to its shareholders and if both companies were rated equally high in terms of potential growth, the potential investor might want to consider the volatility of the two stocks to aid in the investment decision. We will see more numerical examples in class. So we now move to measures of skewness. The measure of skewness are generally called Pearson's first coefficient of skewness and Pearson's second coefficient of skewness. Measures of skewness are used in determining the degree of asymmetry of a distribution. A distribution which is not symmetrical is said to be skewed. Pearson's number one coefficient of skewness is given by Sk equal to mean minus mode divided by sigma. We'll consider numerical examples much later. Then let's move on to kurtosis. Kurtosis is measures Kurtosis measures the degree of pickedness of a distribution. It is usually taken relative to a normal distribution. There are three types of kurtosis. A distribution can be leptokurtic, it can be platykurtic, or mesokurtic. There are diagrams here to differentiate them. The mesokurtic is otherwise known as normal distribution curve. That is, the curve that is moderately distributed. The figures below show the relative pickedness of distribution of data. The first diagram represents the leptokurtic, the second diagram represents the mesokurtic, and the third diagram represents the platykurtic. The moment coefficient of kurtosis is used to calculate the pickedness of a distribution. However, for normal distribution, that is the mesokurtic, The moment coefficient is given as A equal to 3. If the moment coefficient of cortices A is greater than 3, it is said to be leptocortic. And if A is less than 3, it is said to be platycortic. But when A is equal to 3, it is said to be mesocortic. Thank you. See you in the next class.